An inductor, or a solenoid, is an electrical component that can store energy in the magnetic field created by a varying current flowing through it. It is typically a wire wound around a ferrite core. An inductor resists any change in the current flowing through it. Any change in current through an inductor induces an EMF across it. This induced EMF is proportionate to the rate of change of current. According to Faraday's law of electromagnetic induction, the induced EMF in an inductor is equal to minus L di by dt, where L is the self-inductance constant for the inductor and I is the amount of current passing through the coil. This EMF opposes the change in current flow through it in accordance with Lenz's law. Hence, a minus sign as per convention. Now, we shall see how an inductor behaves when an AC voltage is applied across it. Let's assume that the inductor coil has negligible or zero resistance. This assumption is mainly so that we can observe how an inductor ideally behaves. Now, assuming the circuit to be purely inductive, we shall make use of Kirchhoff's loop rule. According to this rule, the sum of potential differences across various components is zero. The voltage across the source of alternating current is V equal Vm sin omega t, where Vm is the amplitude of the AC voltage and omega is the angular frequency and t is the time. Let this be equation 1. Applying Kirchhoff's law to the purely inductive circuit, we get Vm sin omega t minus L di by dt equal to 0. Here, Vm sin omega t represents the potential difference applied across the circuit, and the term L di by dt represents the self-induced EMF in the inductor. Thus, we get di by dt to be equal to Vm by L sin omega t. Let this be equation 2. Equation 2 is a simple differential equation. It tells us that the first derivative of the current with respect to time is a harmonically varying quantity with an amplitude Vm by L and an angular frequency omega. This implies that this derivative is in phase with the applied potential difference. Integrating equation 2 with respect to time, we get the value of the current in the circuit as I is equal to minus Vm cos omega t by omega L plus the constant of integration. Let this be equation 3. Since we know that the voltage source is supplying a time-dependent voltage, which is symmetric about 0, we can assume the same to be true of the current. Hence, we take the constant of integration as 0. Hence, equation 3 can be written as I equal to minus Vm cos omega t by omega L. Let this be equation 4. Writing minus cos omega t as sin omega t minus pi by 2, we get I equal to Vm by omega L into sin omega t minus pi by 2. Let this be equation 5. Now we substitute omega multiplied by L with XL, which is known as the inductive reactance of the circuit. We get the amplitude of the current Im equal to Vm by omega L or Vm by XL, since we know it to be the maximum current value attainable. Hence, equation 5 now becomes I equal to Im sine omega t minus pi by 2. Let this be equation 6. The expression we used earlier for Im implies that the value of current in comparison with the value of voltage is limited by the denominator, which we call the inductive reactance of the circuit. This, by analogy for a simple resistive circuit, can be considered an equivalent to resistance. This inductive reactance is directly proportionate to the inductance L of the circuit and the frequency of the current or voltage. Inductive reactance is equal to 2 pi Lf, which is equal to omega L, since 2 pi f is equal to omega. On close inspection of the expression derived for the value of current in the circuit, we can see that the current lags voltage by a factor of pi by 2 in phase. The phasor diagrams to analyze the relationship of lead or lag between the current and voltage is shown. The current lags behind the voltage in phase by pi by 2 or in time by 1/4 of the time period t. Another observation is that the maximum value of the current in the circuit is achieved at exactly 1/4 the time period of every cycle. Let us now try to see the power dissipation through the inductor compared to resistance. The instantaneous power supplied to the inductor is denoted by the product of voltage with current flowing through any circuit element. By substituting for V and I as in equations 1 and 6, we get P is equal to Vm sine omega t into Im sine omega t minus pi by 2, which is equal to Vm Im sine omega t into sine omega t minus pi by 2. As sine omega t minus pi by 2 equal to minus cos omega t and 2 times sine omega t into cos omega t is equal to sine 2 omega t, we get power P equal to minus Vm Im by 2 into sine 2 omega t as shown. Let this be equation 7. This instantaneous power evaluates as a time-dependent harmonic function. As this is a time-dependent sinusoidal function, its average over one complete time period will be 0. The argument of sine function for voltage is omega t, and for power is twice omega t. Hence, the time period for the power function is half the time period for voltage. Since the average value of sine 2 omega t over one complete cycle is 0, the power supplied to an inductor on average in an AC circuit over one complete cycle is 0. This can be seen as displayed by the plot of power supplied versus time. Variation of voltage and current with time is also plotted on the same graph for comparison. As the inductor is nothing but a coil of wires, it is structurally the same as an electromagnet. Hence, when the current flows through the coil, it is magnetized and demagnetized depending on the direction and magnitude of the current in the circuit. Variation of magnetic flux with time too is plotted on the same graph. As shown in the graph, we will study the magnetization of the inductor in the 4 periods marked in the graph as 0, 1, 1, 2, 2, 3, and 3, 4 respectively for one complete cycle of voltage or current. As in the first time interval 0, 1, the value of the current keeps rising from 0 and reaches its peak value at 1/4 of its time period. The flux passing through the coils change, setting up a magnetic field as shown in the figure. The current enters the inductor coil at A and leaves at B. As the current and voltage are both positive, it means the power is positive. Positive power means the inductor is absorbing energy from the circuit. In the second time interval, 1, 2, the value of the current keeps decreasing from its peak value at 1/4 of its time period and reaches 0. But it always remains positive. The flux passing through the coils change, decreasing the magnetic field setup as shown in the figure. As the current is positive while the voltage has become negative, it means the power is negative. Negative power means the inductor is releasing energy to the source, which is the circuit. During the third time interval 2, 3, the values of both current and voltage are negative. Since the current has become negative in this interval, the flux passing through the coils change, setting up a reverse magnetic field as shown in the figure. In this case, the current enters the inductor coil at B and leaves at A. As the current and voltage are both negative, it means the power is positive. Hence, energy is being absorbed by the inductor. During the last time interval 3, 4, the value of the current decreases and reaches 0. As the current is negative, while the voltage is positive, it means that the power is negative. Hence, energy is again being released from the inductor. This cyclic discharging and charging of the magnetic field of the inductor in reverse polarities keeps on taking place as long as there is AC current flowing through the inductor. Thus, the instantaneous power in the inductor is positive when both the instantaneous voltage and the instantaneous current are positive or both negative, and the power is negative when any one instantaneous voltage or instantaneous current is positive and the other negative.